Bonjour, sorry, hi everyone. Welcome to this workshop on ML-assisted sampling and in particular application in physics. We are pleased to have all of you here and all of you online if you are following us. This first session will be chaired actually by Tony Lelièvre, one of the co-organizers, with myself, Marie-Lou Gabrier and Valentin de Bortoli. So I will leave the stage to Tony to present our first speaker.
Thank you, Marie-Lou. I will be short. So the first talk will be given by Pierre. So you don't have a mic? Non, mais le micro, tu l'as pas. Okay. So I will leave the mic to Pierre. So the first talk will be given by Pierre from Sorbonne University. And he will talk about an adaptive reaction coordinate to the modelization of the main protease in SARS-CoV-2. Thank you, Pierre.
Merci, Tony. Thank you, Tony. Thank you, Marie-Lou, and thank you, Valentin, for the organization and the invitation to this workshop, which will be very interesting, I guess, based on the speakers, excluding me. Okay, so indeed I'm going to talk about, so the main point of my talk is that it's more about an application of a class of algorithm that really about a very specific algorithm, which I believe is really the best one in this class of algorithms. So it's a work with all this bunch of people, so I'm not going to go in each one of them. As the only thing I want to say is that it's a very multidisciplinary work, because so I'm the only mathematician in the team. Basically, I wrote the algorithms that I'm going to present later on. Then here, Théo Jaffrelot-Inizin and Frédéric Sellers are the main workers of this story. So they were doing their PhD at that time with Jean-Philippe Pigmal. So there are people from theoretical chemistry, computational chemistry. The computations were running on the supercomputer Zhang. So you had questions of high performance computing. So you have people here who are you are specialists of HPC, and then at the end you have a long trajectory of some biological systems, and so you had to make sense of it. And so you have people more from biology, biochemistry, who post-process everything. So it was all this work together. And okay, so I'll start. So I don't know who is coming from which field. Some people completely know everything. That some people can come here and do the talk at my place. Okay, so maybe some people are less familiar with some topics. So I'm just going to go through some very fast, briefly, on some generalities on what we are trying to do, and then I'll go specifically to what we've done. So basically, what we want to do is sampling. So we want to compute an expectation of some function with respect to some measure. Or in other words, we want a statistical sample of a probability measure mu. Okay, so mu being given by its density with some energy u and some inverse temperature beta. And so what you want to do is you're in high dimension, so you want to do Monte Carlo methods, Markov chain Monte Carlo methods. And here, in our case, and which is pretty basic in molecular dynamics, the xk here, so the trajectory along which we are going to do this empirical average. Okay, so we are going to sum this test function over a trajectory xk, and the xk will be a discretization, a numerical scheme based on the Langevin diffusion, which is this stochastic differential equation, so which is basically the Hamiltonian dynamics plus some heat bath to ensure ergodicity. So, well, anyway, this it's not important. So we are running this trajectory, and each time we are keeping the snapshot of the position, and at the end we are just doing some statistics on this trajectory. So basically, this is the general problem. As many of you, if not all, know, the typical kind of problems you have in this problem of molecular dynamics is that you have a metastable process. So you have the target mu, the measure mu, is multimodal. You have several places which have a high probability but which are separated by low probability regions. So you have modes, several modes, and you want to see each of them, but then the Langevin diffusion will typically take a long time to see a transition from one mode to another. So to go from one well, you see, so this is a local minimizer of the energy, and to see a transition from here to here is very long. Okay, and so you have a problem of time scales, because on the other end you have so in molecular dynamics, for instance, your system, your energy U. So in my case, will be given by empirical potential. So meaning that you have an energy which is typically the sum of pairwise interactions. So you have several atoms, they interact with potential, and typically the potential is singular at 0. So you have a singular repulsion of nuclei when they are very close, and so you have, which means you can have forces which are very high, and since forces are very high and forces are here in the drift, it means that you need a step size of your numerical schemes which is very small. So typically the time of the one numerical step size is 1 femtosecond, and the typical time to see the transitions you're interested in can be of the order of the millisecond, and so you need a number of iterations of your simulations which are possibly prohibitive. Okay, and so you have this kind of problem, and typically you are trying to see a rare event which is such a transition from one mode to another, and so there is a large literature about rare events, and one way to deal with them is to do importance sampling. So now, again, for people who are not familiar with this, a very sketchy presentation of importance sampling. So let's forget the Markov part. Let's say we are doing Monte Carlo, just so we want to compute an expectation with respect to a measure mu, and we random variables which are distributed according to mu. So let's say we can do that. So the Monte Carlo method tells you because of the law of the large number, this is going to be approximately what you want. Okay, but let's say that xi are almost all 0, and only a few of them is 1. Okay, so you have a very rare event which is to see a 1. And if you do that, most of your sample will be useless because it's basically 0. You know that it's mostly 0, and so you are just waiting for someone to appear. And in that case, what you can do is, instead of doing the real experiment you're interested in, which are random variables with low mu, you do a biased experiment. So let's say with a low mu tilde. So let's say you do an experiment where you have more ones than in the initial one. And then you interpret the expectation with respect to mu of the function f as the expectation according to mu tilde of f, but reweighted by exactly the ratio between the two measures. Okay, so so now this is a real equality, and now you can do a Monte Carlo method based on this. And if you have chosen mu tilde well, you will decrease the variance of this because you will see more of the rare events, and so you will get a good sample for mu tilde of the rare events faster than mu tilde. Okay, so now how do you construct a mu tilde in practice in molecular dynamics? So there is a whole family of such importance sampling strategies which are based on having a good reaction coordinate of your system. So again, reaction coordinates are going to be thoroughly discussed in the rest of this workshop. So I'm not going to say anything clever here. I'm just going to give a rough definition for people who are not familiar with this, if there are any in this room again. So basically, it's just a very low dimensional representation of the system, because basically our simulation, we do it for all atoms. So each atom has its 3 coordinates in the Euclidean space. Okay, so you have a system in dimension 100, several thousands possibly. But in fact, the real process lives in a very much smaller manifold, manifold of a much smaller dimension. And so you are not interested in the fact that this hydrogen here is oscillating through the whole simulation. Okay, you really don't care about that guy. You care about, you just want to know in which mode, in which local minimum you are. Okay, and then you have some oscillations around this minimum, but you are really not interested into that, and so you just want to have good parameters which tells you exactly in which mode you are, and you want as few as possible such coordinates. So here, this is a very classical example of the alanine dipeptide. So you have a bunch of coordinates, but you can describe it pretty well with either 2 angles or 4 angles possibly. And so you see you have here, maybe it's not completely clear for all of you, but here you have 3 configurations which are macroscopically different. So you really have a torsion in the molecule, so you have something really different. And it's, again, you don't care about what is doing this hydrogen, you're just doing the angle, you know in which typical configuration you are. Okay, so this is a reaction coordinate. Mathematically speaking, it's a function which takes into takes as a variable the whole configuration of the system, and which gives you a few coordinates which are those quantities. Okay, and so just not to adapt important sampling, now we are doing a trajectory, a Markov chain, Monte Carlo method, and the only difference. Okay, so what have I done? Okay, so the only difference now is that you don't know exactly, you don't know the normalization constant of your target measure. That's why we are doing Markov chain Monte Carlo and not just Monte Carlo. We cannot sample exactly a guy according to mu or mu tilde. We just know that the weights are proportional up to some constant that we don't know to this ratio of the steps. But this is enough to get something which is convergent for a large size of the sample. Maybe I forgot to say here in that case, it's written here, this estimator is unbiased in the sense that its expectation is exactly what you want to compute, which is not the case here, okay, because you are doing the ratio of 2 unbiased estimator, the ratio is not unbiased. And so there are a bunch of variations of this idea to have algorithms. So you have metadynamics, adaptive biasing force, umbrella sampling, and variations of all that, etc. So, okay, so this is a very rich field, and I'm not going to go into details here. Okay, so now I just said if I have reaction coordinates, I can do important sampling, and so I can have a good sample of my biased measure, but then I know how I biased it, so I can unbias it. Okay. And now the point is, okay, what if I don't have any reaction coordinates? And this will be the topic of some talks of this workshop. And you will see that I'm going to do something very basic, but the idea is that, okay, if I don't know a good reaction coordinate, because I don't know my system, I don't have any physical or chemical intuition of what is going to describe the different minima. Okay, there is a strategy. Now there are works that tells you, okay, give me a sample of your measure mu. I can give you a reaction coordinate. Okay, so a non-supervised definition of reaction coordinates. And when you have these 2 blocks, of course, you want to do something adaptive. First, I start by sampling without any bias. I have a sample, so I can define a reaction coordinate. So I can use this reaction coordinate to bias a new sampling, which is going to go to beat a bit of metastability and explore new regions. Though I have a new sample, I can update my reaction coordinate, and so I'm doing this. So I can take any of my favorite important sampling scheme, and I do this adaptive scheme. Okay, so and this is what we did. And I already jumped to the conclusion. The reason why I wanted to present it here, it's not because there is a lot of machine learning here. In fact, so there won't be much machine learning in my talk. In fact, it's because we did something very basic here, because we had in mind the application and not to do the best thing. And I knew that people were working on that, and in particular, the talk of Gabriel Scholz is doing exactly the same thing, but in each part, you have a block which is strictly more sophisticated than what we did. Okay, and so my point here is that so I wanted to present it here because there would be people who worked on that and who would tell me what I should do here instead of what I've been doing. Okay, all right. So as I said, my point is that about the applications. Okay, we made the thing work on a real scale problem, but it didn't start with, okay, I have an idea of an algorithm, I write it, I test it on a WAD problem, etc. Okay, we jumped directly to the context, which is the following. Okay, we started with this. The beginning of the project was so in March 2020, which was more or less the beginning of the pandemic, and so everybody was simulating parts of virus because yeah, we had to understand how it worked, and people had to test some candidates, some molecules to see how the virus reacts in front of which molecule. Okay, so what the goal of the team was to sample one part of the virus, which is the main protease, which is which was identified as an important part to test. Okay, in water. So the whole system, protease plus water, was 100,000 atoms. The goal was to run it on the software which is developed by the team I'm working of computational chemist of the LCT I'm working with, which is Tinker HP, and the one of the characteristics of this force field with respect to this software, so it's a software of molecular dynamics, it does many things, it's used by practitioners, and the point with respect to other similar things is that it uses a polarizable force field. Okay, so either you know what it means or you don't know. It's not very important. But the consequence is that it's very costly. It's more costly to compute forces with polarizable force field. So it's meant to be more accurate, but more costly from a numerical point of view than non-polarizable force field. Okay, it's supposed to get a bit of quantum effects, at least to mimic them. Okay. Well, anyway, so it's something a bit more costly to do one trajectory. And okay, the consequence that one of the consequences that we wanted to use that is that at that time, so in 2020, all the metadynamics, ABF, etc., all this dictionary of methods was not available in there. Okay, and so we couldn't use them. And in fact, recently, in particular with during the PhD thesis of Lise Morin that we were advising with Tony Olièvre and Jean-Philippe Picmal, with the work of Louis Lagardet and Jérôme Hénin, now you have the package Colvar, which is full of this kind of methods, which is talking with Tinker HP. So now if we want to do the same, as now we wouldn't do maybe we could do something else, again, which is related to this first part. Okay, so, but now there is the other part. And okay, in this system, we had no reaction coordinate. At least a chemist told me that we had no reaction coordinate. I'm not going to be the one to have a chemical intuition on that. And the last part is that it was going to run on the supercomputer Zhang, so you needed an algorithm which was, which could, the algorithm is not designed for a particular structure, but it's designed to run on something parallel, and yeah. So it was part of the considerations in the algorithm. So now I'm going to describe the important sampling scheme that we did. And for this, I'm going to first present a reference experiment. Okay, I'm not going to do Markov chain Monte Carlo. I'm going to do Monte Carlo. Okay, so I will really have a non-biased estimator. So first, I present you a reference a random experiment, and then I explain where I do a bias and how I know exactly how I'm biasing. Okay, so the initial one is like that. So you start with N0 configuration. So if each of these guys is a system of 100,000 atoms, you run a non-biased Langevin trajectories. All those trajectories are independent, okay? And then you take snapshots of all those trajectories. So every 10th time step, I don't remember, you keep the configuration in memory, and then you completely forget the dynamics. Okay, now this is your sample. This is your current best guess of what is mu, what is the distribution mu. And you say, okay, I'm going to start again new configurations, and to do that, I just select randomly, independently, and uniformly over the empirical distribution. I start with new initial conditions, and I repeat. So I do Langevin trajectory, snapshot, etc. And so I have a sample which grows, etc. And just a remark that when we forget the dynamics, we forget who was here at the previous step. Okay, we are just accumulating points, and after 10 iteration, we can start with a guy which was an initial condition at the very beginning of the simulation. It's not crucial. We could do something else, but this is what we did. Okay, so just to say, this is a reasonable experiment. Okay, anyway, we know that with the numerical resources we have, we are not going to. Okay, maybe I won't. Okay, we are not going to have n go to plus infinity here. Okay, so we are not going to have a long time convergence. So I just want something which is unbiased with respect to this. Okay, and so of course this is biased due to the initial condition, and I'm not going to beat that. Okay. No.
Sorry, can I ask you?
Yeah.
If you keep sampling, say the same number, it's asymptotic. It's just going to be a slow convergence like 1 over t. But
Yes.
the bias will go, right? You said it's biased, but it's
So
perfectly fine in the limit, right?
So the question is, if I keep resampling with people from the beginning, I have a convergence which is 1 over t, while
So that's you were saying that it's biased.
no, yeah, it's unbiased. So the result I have, so if I let go to t to infinity in my scheme, the variance will be 1 over t, but the bias will be 0. Okay. But anyway, I'm not going to let t go to infinity.
No, it's, yeah.
Yeah.
I'm trying to understand what you meant by bias, but now I
Yeah.
understand.
And now, if you do Markov chain importance sampling, to make sense, I mean, you really need the two guys to converge. So, yeah. So this is what I. But what I meant with bias here is that the expectation of what I'm going to do is equal to the expectation of this reference measure. But this reference experiment. But this one is biased because if I run it for some time t, there is a bias in 1 over t because of the initial conditions. Yes.
Now I understand.
Yeah. So now, okay, so the importance sampling I'm going to do is just at the point where I select the new initial conditions. I'm just going to select them depending on the score, and the score depends on the position of the configuration. Okay, and so I just have to explain how I compute this score, and you have the scheme. So first, and this is where I'm doing something very basic, and I'm waiting for people to improve this, people or me, but I just have to see what you're all doing. We just did a principal component analysis of our configurations. It means that we only consider linear reaction coordinates. ASSAI is a function which is linear. We just do a linear PCA of the sample, and we keep, and our modes are the, so in our case, it's the 4 first modes, and 4 is motivated by, is motivated by, so you compute the percentage of variance which is explained by the modes, and you stop when you are around 50. So this is at the beginning of the simulation and at the end of the simulation. So 4 was reasonable here. Okay, so we have a reaction coordinate which is just given by this, and now here goes the computation of the score. Sorry. Yes.
So this reaction coordinate is going to favor big movements.
Yes.
But is this? So I don't know anything about this system. If that makes sense if you're interested in folding or unfolding, but maybe not for some conformational changes.
So, and that's precisely why you shouldn't do that. I mean, that's precisely why. Okay, again, it's something we did because it had to run, and this was available. It's clear that you have to think more about what you want to do for your reaction coordinate. What we wanted to do was exploring. So anyway, yeah, so you want to explore, and your good reaction coordinate for us in this sampling case would be really something which for each mode of the reaction coordinate correspond only one mode of the initial configuration. Okay, and this is okay. It's not clear that this is a good thing, but at least we were trying to explore a bit while staying only biasing in a small dimension, which is important for. Otherwise, the mu tilde, the reference mu tilde, is way different from mu, and you are completely doomed. But indeed, precisely, this is very basic, and it's clear that at the end of this workshop, already people know here that you should do something else, and at the end I will know that what I can do. But you are right. It's not the target is not the reaction target. Coordinate target is not. It could be more clever. Okay. So now let's say I have this reaction coordinate. What I do is I just look at my configurations in the space of my reaction coordinates, and I estimate the density in this space, and I'm going to select people at a probability which is proportional to the inverse of the density in this low-dimensional space. Okay, so what is the motivation? So if you think of a finite set, if you had a finite number of values for the reaction coordinates, you have points which are over 1 over k, and if you select an index, if you select the index of some sample at a probability which is proportional to the inverse of the number of guys who are at the same site as high. So what is the probability that you take the site number high? It's the number, you do the sum over all the particles which are at the value I, multiplied by the probability that you select one of them, which is exactly 1 over the number of guys. So you divide the number of guys by the number of guys, you get something which is independent from the number of people who are at the value I for the reaction coordinate, given that there is at least one guy. And so when you do that, you exactly sample the uniform measure over the support of your sample. And now if you do something a bit between this finite set and what we are really doing, so if you had an explicit density, you do a IID sample with low nu, and you select an index with a probability proportional to 1 over nu. You can check, and basically it's the same thing. You can check that as the sample goes to infinity, your initial condition given by this bias selection is going to converge to the uniform measure. And that's what we want to target. We want to target something which is not multimodal, so that you explore all the configurations. And if you have seen, because the idea is that if you have seen all the configurations of psi of x, you believe that you have seen all the important conditions of x. Okay. So I'm going to so just a sketch. You have your sample. First, you estimate a density in a 4-dimensional space, and then you do a bias selection, which is depending on the density. So people who are in a low density region are more likely to be chosen, and this is done in such a way that if you have two areas of the same Lebesgue measure, and you have a lot of people here and a few people here, in fact, the two areas are going to have a probability 1/2. Okay, this is basically what we are targeting. So in practice, we didn't let go to t to infinity because we did 15 iterations of that. In particular, we were not really interested in. I'm thinking of the work of Gabriel Stolz and his co-authors here. The reaction coordinates was just an internal tool. We were not interested at the end on what was our reaction coordinate. So here is it. But the only thing we have, is that we know that it is really unbiased with respect to the initial experiment, which is itself unbiased with respect to the truth, which is the Gibbs measure. And just a remark is that we are accumulating important sampling weights, because if I select someone a new initial conditions whose past in the past of which there were already selections, the weight is going to multiply. Okay, so if you run this algorithm for long, you have trajectories. We will have weights which are very low because you will have many unlikely events before, and you will have a problem. And it's a typical kind of problem you have when you want to do important sampling based in Gersanoff theorem to do trajectories. And at some point, for a long time, you don't want to do that. But we are not in a long time, so it was okay for 15 iterations. And just a few results. So indeed, we just wanted to spread things in this 4-dimensional space related to variance. And so what you see here is a comparison with two previous experiments, which were done a bit at the same time, but slightly before us. So what you do, what you see in so in blue here and here, it's one previous experiment. In red here and here, it's one previous experiment. And in the back, you see our experiment, and this is after 2 days. So here, this is after 2 days, and this is after 12 days. So the whole experiment, and we just plot what happens in the 2 first modes of our reaction coordinates, and you see that basically in these 2 modes, which are what they are, okay, PCA. After 2 days, we had seen everything that the other guys had seen, and after 12 days, we had seen more things. Just a remark: those experiments were done with non-polarizable force fields and not the same. So everybody is not targeting the same physics. So we are not doing exactly the same U. So it's not okay. It's not, but we are trying to do the same chemical physical system. So okay, it should be a bit similar. Okay, I'm not going to go into the post-processing because it's more the work of my colleagues. But from this, you don't really care about the distribution. You just want some typical example of each mode. So we did clustering. So we did see. So here we had. So this is the 2 previous experiments, and we did see configurations which were not seen. And then you have a work of explanation. And okay, the only thing I can say here is that my colleagues were happy, and they found some interesting things to say about the difference between clusters and for cryptic areas or things like that. Okay, I'm not going to go into details, but at least they were pretty happy with the result. I'm just going to conclude because my time is up. As I said, you have 2 blocks. Okay, the adaptive ID is very natural. You have to choose your important sampling. You have to choose your the way you define your reaction coordinate. Now we have, instead of 2 years ago, now we have a lot of methods which are available in this software for important sampling. And up to now, we have nothing for reaction coordinates. Also, the part with our important sampling is somehow basic, but it's very good for parallelism because nobody is talking with nobody during your Langevin trajectories, and you just have to get everybody back to just to do this small density estimation and selection. Okay, but you have much less communication that if everybody had to give a bias to everybody at each time step, okay, etc. So it's simple and thus robust to architecture of the hardware you are running your simulation. But I really think that okay, we should we will. So the conclusion is that I think this is a very good application for the works that some of you have been doing and some of you are going to present here for unsupervised determination of reaction coordinate. And with this, I thank you for your attention.
Thanks for the talk. You were very short on the results and why your colleagues were happy. Can you elaborate a bit more on this?
I can elaborate a bit. But not too much because really it's not the part I am very comfortable with. So first, there are configurations which were not in the previous experiments. They had a configuration which was in agreement with an empirical work which was not explained. So okay, it's a very high level what I'm saying, which was in particular, I think this is about this part here. So which was in agreement with an empirical study, which was not really not explained. It could not be explained with configurations found by the 2 previous experiments, but it's not clear whether it's due to the sampling or if it's due to the polarizable force field part. And also they found, so they were interested in cryptic pockets. So which so maybe some of you know that more than me, but surely. But it's some parts in the protease in the molecule where you have some area, and so water can come, or water or another molecule can come and interact within the molecule, and so they had found new pockets which were again not found by previous experiments, and these pockets can be used then for screening candidates when you want to see, okay, I try to have a molecule which interact with that. You can put it at the exterior of your molecule and compute some energy of interaction, but you can also put it in a cryptic pocket and see what happens. Okay, so I don't want to say something completely false here, but this is a kind of a post-analysis. So the post-processing of the data is, I think, it's more than half of the paper, and really it's not the part I can go in much more detail. I understand that this is not a very good answer, but okay. At least 2 examples of things, both related to empirical works and yet to finding new theoretical explanations of some difference of conformation. So here, okay, this is a particular, so this is a difference of some active site, I don't know where here, and you see that between different clusters, you see something different, and if you do the clustering here, you with the 2 other guys, you don't see this variety. Then, okay, how much of that, so this is what you get from the simulation, on a polarizable force field after 15 iterations of our etc. So what of it is related to the true what happens in practice? Okay, apart from the comparison with some empirical works, crystallography, etc. So again, I don't have a very clear vision of to which extent we were more. Okay. If you take all the empirical studies and you want to see if you are doing strictly better than the 2 other guys on being in accordance to being in agreement with the empirical studies, I cannot tell you that. Okay, I cannot be quantitative here. But maybe I can check again the paper and go back to you to see the details.
My question is mostly a comment. I am in the field of computational biology and chemistry, and I want to say that PCA is a good start to see some key motions of the protein and maybe get some information about what you could use then for featurization of a neural network, for example. So what kind of input you will give instead of giving XYZ coordinates of all the atoms. And also sometimes you can even see some important motions in kinases, for example, like a twisting motion or a hinge bending motion. So all this you can see with PCA. So I understand why you managed to observe the opening and closing of cryptic pockets. However, you observe them in the C-terminal that is very flexible. So I wouldn't trust these results very much.
Okay. Thank you. So thank you for this positive comment. It makes me think of another comment, which is if you use a sample to define a reaction coordinate, anyway, the reaction coordinate is going to explain your sample. And so if you're trying to discover something new, which is not in your sample, so let's say you have 2 modes. You have 2 different modes, and so what increases the variance is to take the reaction coordinates which distinguish these 2 modes, because you will have half people here, high variance. But as long as you have not seen this mode yet, when you are doing PCA, you are doing the local variance of your local minima. So of course you cannot hope to get from a sample which don't have the full information. Okay, you're just going to your reaction coordinate is going to take the information which is in your sample, and so which is a bit related to this.
Are there more questions? Thank you very much, Pierre.
Thank you.
So let's take a few minutes to switch computers. Yes, please. Few technical arrangements.
Ah, j'ai gardé le micro.
Ah yes.
Hop.
So now we will have a talk given by Jutta Rogal from Germany or the US? The US actually, no?
I'm in New York right now.
Yeah, from the US. So she will be talking about pathways in classification space, machine learning collective variable for enhanced sampling. Thank you very much, Jutta.
Thank you very much, Tony, and thank you very much for inviting me to this workshop. I'm very excited to be here. So I'm not a mathematician. I'm a physicist, chemist, computational scientist, somewhere in this. But I'm very much interested in the development of new methods, and it's always a pleasure to discuss all these questions with people on a more fundamental level of developing the different theories and methodologies. Yeah, I'm currently in New York, actually at New York University. I also have an affiliation with the Freie Universität in Berlin, kind of like splitting my time in between these two places, which is also very exciting and very enjoyable. And today I would like to talk to you about some things that we've done in terms of trying to obtain reaction coordinates from machine learning classification and then use those in enhanced sampling. And we already had in the first presentation a very good overview about the different problems that might arise in these type of things, in particular in determining reaction coordinates and biasing the system and so on. So the type of questions that we are interested in terms of structural transformations is, for example, nucleation, which is the initial step of crystallization. We have homogeneous versus heterogeneous nucleation. We would like to control, for example, polymorphism through seeding or through the environmental conditions and so on. And of course, as everybody, or not as everybody might not know this, but nucleation is one of these challenges in computational physics because it is one of the things that we call rare events, which means that if we're trying to sample this with regular molecular dynamics, we're never going to see it simply because the time scales we would have to cover to observe a nucleation event is way too long. No? Other things that we are looking at are solid-solid transformations. For example, this is actually an experiment in a colloidal system, in a 2D colloidal system over here, where you have a solid-solid transformation, again, a nucleation event, and then you have the formation of interfaces here, and you have the migration of the phase boundaries. And again, if you are interested in doing a molecular simulation of such a phase boundary migration, again, you run into the problem of the rare event that you will not really see anything because all the, let's say, all the time scales, all the involved time scales over here for such a phase boundary to migrate are much longer than what you would be able to see in a molecular simulation. And so this rare event problem, this timescale problem, comes from, of course, from the let's say the topology or the shape of our free energy landscape. So if you have just like this projection over here, again here, for example, if we project everything onto a one-dimensional reaction coordinate, and we look at our free energy, then of course we have some sort of like metastable states on our free energy landscapes. We have barriers in between, and very often we are not so much interested in the wiggling around in one of these metastable states, but we are much more interested in the transition between the metastable states. So again, if you think about nucleation, this would be your liquid and this would be your solid phase. So you can sample the liquid very well, you can sample the solid very well, but what you're actually interested in is in this transition process, and that you're not going to see very often because you have to overcome this high free energy barrier. No? And so what we're using then is, of course, all kinds of different enhanced sampling schemes. We have biased, we have unbiased sampling schemes. We have things that try to preserve the dynamics. We have things that are mainly interested in sampling the free energy surface and getting the right thermodynamics in the system. And depending on what you're interested in, that will sort of like determine what you can, or what kind of methods you're going to use. Also, whatever you want to use, and that's what we're going to come back also later, if you need to already have a projection into a low-dimensional space, then of course, again, it depends on how much you already know about the system and if you can come up with a suitable reaction coordinate just by yourself, or if you need to first sample this. And this is the problem that also Pierre was talking about in his presentation, is that, well, if I have all the data, if I have a lot of sampling data over here, I can analyze those and I can extract from all my data some sort of collective variable, and then, or like a set of collective variables, and then maybe from that do a good projection onto like some sort of reaction coordinate. But then if I want to use this in sampling the free energy landscape in the first place, then of course I'm running into this chicken and egg problem that I need the data to extract the reaction coordinate, but I can only get the data by sampling along the reaction coordinate. And what Pierre was talking about is these type of iterative approaches where you start with something that appears reasonable. You start sampling, you do an analysis on the data that you have, you suggest a reaction coordinate, you continue your sampling with your hopefully better reaction coordinate, you create more data, you do more analysis, and so on, and you do this in an iterative way. Now, another idea that came up a couple of years ago is to use the classification of the different states, the different metastable states that you are interested in, and then essentially what you're doing is that once you have this over here, once you have some sort of a classification scheme between the different states, you can then use the decision function between these different states as your collective variable to push the system between the different metastable states. And this is essentially what I will be talking about in my presentation today. And so one of the let's say maybe the first applications of this in molecular simulations was published a couple of years ago by Sultan and Pandey over here, and this was with again our most favorite dummy molecule over here, the alanine dipeptide, and you wanted to do like a two-state classification over here between the two states of the alanine dipeptide essentially in the system. And so what they used here, so they actually did different things. So what I'm showing you here is where they used just a simple feed-forward neural network where you use as an input to your neural network, you just use the sine and cosine of your dihedral angles over here, and you just do a two-state classification in the system. And the only information that you need for the classification, and that's now the advantage or the advantage that you have when you're using this, you only need data in the stable state. So you need, for example, in this case, the training data that you can see here were obtained in this basin over here. So this is this 5 psi diagram of the alanine dipeptide where you have these different minima. So you only need to sample the basin over here. You need to sample the basin over here. Based on these data, you train your machine learning classification engine, and this will come up with a decision boundary in your feature space, in your space of input variables over here, which you can see in this plot as the slightly the light red and light blue areas over here, which are essentially the classification areas for these two states of the alanine dipeptide. And then you can use the output of your neural network, so the decision function of this neural network here, as your collective variable. And in this case, they used well-tempered metadynamics, and you can see that they can actually, using this decision function, essentially, they can bias the system to go back and forth between the two different states in your alanine dipeptide. Similarly, in like 2 years later, there was a paper by Bonatti and others, and again they used to use a neural network, but in this case they didn't use a neural network for the classification. But what they did is that they said, okay, well, we're just going to use a bunch of input parameters. We don't really care, a huge list, and then we used the neural network essentially as sort of like a dimensionality reduction. Right, so we can do a nonlinear combination of all our input parameters over here, we come up with something in a reduced representation from our input features over here. And then in this space over here, the way that we're training all of this together, we make sure that our two states are linearly separable. And then we can just use something like the linear discriminant analysis to do our classification. So it's one step in between. So if you look at these pictures over here, so this is your data essentially in your descriptor space, as your input space to your neural network. This is the reduced representation that you get by a nonlinear combination of your input descriptors over here. And you can see that in this space, of course, you can very nicely linearly separate your two states over here. And again, they were running this on the alanine dipeptide. And this graph over here shows you the different lines for your classification. So the dashed lines over here are the classification of your two states, this one over here and this other one over here. And they did like a back representation of their linear discriminant analysis decision boundary of the isolines onto the phi psi representation of the alanine dipeptide. So this were all, these two examples are these small molecules and a two-state classification. Now the type of problem that we are interested in, as I was initially introducing, is trying to sample the migration of phase boundaries, for example, between these two different crystal structures over here. So this is a body-centered cubic structure. This is a topologically closed-packed phase over here. And this is interesting in all kinds of different systems. For example, if you have this in pure tungsten, you have the very interesting situation over here that the body-centered cubic phase is very interesting for microelectronics because it has a fairly low resistance in the body-centered cubic phase. And then the A15 phase, that's very interesting for spintronic devices because it has a very large spin Hall coefficient. And if you grow these tungsten in thin films, depending on what you do, you can either promote the formation of this A15 phase or of the BCC phase. And also, of course, you will see a transformation between these two different phases. And of course, you would like to understand how you can control let's say the transformation between those phases and end up with the one that you actually want. And so if you have a condensed phase system and if you want to sample the phase boundary migration, then of course you cannot easily come up with a global collective variable that can easily describe this transformation process over here. In particular, if you think about how this transformation might proceed, then of course you have a bulk phase over here, you have a bulk phase over here, then you have the interface region. And if you think about phase boundary migration, then essentially you need to be able to sample and drive the local, or let's say the local changes in the structure at the interface region over here. And so the way that we're doing this is that we're also using a machine learning-based characterization of the local environments to do our classification over here. Then based on that, we can define global from, let's say, a situation over here where you have a little bit of BCC and a lot of A15 to a lot of BCC and a little bit of A15, so driving the phase boundary along this direction over here. This can then be described as a path in your classification space or in your space of global classifiers, and that again will then give you let's say a good reaction coordinate that you can plug into your favorite enhanced sampling scheme that you have. So as I said, so we are using a local classification in our system. So that means if you think about your system, what you're doing is that for every atom, you're cutting out an environment of a radius, of a particular given radius, and this is, of course, a parameter that you need to tune. Then you featureize this environment over here based on your local on your central atom over here. This is what you feed into your neural network. You do your neural network stuff. And then you have, in this particular case, a multi-class classification problem over here where the output is all your different structures that you have in your system. And this is, of course, just supervised learning. There's nothing particularly fancy about it. The most important part, as in many of these machine learning approaches, is let's let's say, the evaluation or the selection of the input features that you have in your classification neural network. And so if you want to choose a suitable set of your input features, G over here, again, if you think about a condensed phase system, there are a bunch of requirements that you have if you want to come up with a set of suitable features. One thing that is very important in this type of systems, of course, is that they need the input features need to be invariant with respect to translation, rotation, the exchange of identical atoms, and so on, because otherwise that it would just be, well, it would just become not very expensive to train all of these symmetries into your machine learning approach. Another thing that you need to consider if you want to use this in enhanced sampling is that they need to be differentiable, right? Because if you want to use it in a biasing scheme in some sort of reaction coordinate derived from these input features, then of course you want to have, or you need to have the forces, so that means that all of this needs to be differentiable. Preferable, this has a simple functional form for computational reasons. Also short range should be good because, again, for computational reasons, as well as the total number should be hopefully not too large, again, because otherwise everything just gets very, very expensive. And then you need some sort of like a smooth cutoff function. For example, you can use something like this over here, which determines your cutoff region. So the type of input functions that we've been using for our condensed phase systems, they were originally, or these type of symmetry functions over here, they were originally proposed in the context of machine learning of potential energy surfaces. And in particular, you have these different types of symmetry functions, like one set that is based only on distances, so the so-called like radial symmetry functions over here, where this one is a simple coordination number. This one here gives you essentially peaks on your radial distribution functions that you can place with this Gaussian over here. This one, as you can see, it's kind of like you kind of enhance or reduce certain peaks in your radial distribution function. So this is all based on distances in your system. And then you also have angular symmetry functions, which are based on angles between three of your atoms over here. And these work quite nicely, but for our structure identification, we actually also included input features that are based on Steiner bond order parameters. And the reason for that is that the Steiner bond order parameters are one of the key descriptors for structural, or to distinguish different structures in condensed phase systems, which have been around forever and which work very nicely for a lot of problems. But if you have more complicated structures, they don't work as well anymore. You can't find a good separation. But still, using those as descriptors in our input function, as descriptors as input to our neural network, they actually work pretty well, simply because they explore the local environment based on the spherical harmonics, so they give you a lot of information about the angular environment in your system. And so we did this for the system over here that I've been talking about, and we actually didn't use any of the angular ones. We used 3 of the Steiner input parameters, and we used 11 of the radial symmetry functions, 8 of this very simple G2 function over here, which was essentially placing little Gaussians on the peaks of your radial distribution function, and then 3 of these other cosine type of functions over here. So in total, we only have 14 input functions. So this is very good. It's a very small number, and it's not super expensive to compute this. And then the output that we wanted to distinguish in between. And so you get like an output, let's say an output value for each of these 5 classification things over here, to determine the local structure around each of these atoms.
I have a very nice question. So here you want to monitor the interface?
Yeah.
So for example, on the picture above, what is y?
I'll have a picture where I'm showing this more clearly in like the next slide. Maybe I show this first, and if you still have your question, maybe we'll come back to that.
Just a question about the classifier. So at the end of the day, you get a relative probability to be in one of those 5 phases, or is it?
So you can do it in 2 ways. So you can either say you can do it as a to like a classification problem that you say to one of these classes or any of these classes. So we did it in this way. So it just depends on how you define the loss function. So in this case, essentially any of the outputs could have a value between 0 and 1. In this case, everything adds up to 1, so it's the probability to end up in one of those classes. In this case, it's kind of like the probability to belong to any of these classes in the system. And so depending on, again, what you would like to train or how you would like to train your classification model, that essentially just depends on how you define the loss function for your particular system. And that also then comes together with functions in particular for the output. So in this case, if you have, if you want to do a classification to belong to just one of these classes, the activation function for your output layer needs to be the so-called softmax function, which guarantees this normalization to 1 as the sum over all the outputs. Whereas if you do like your output belongs to any of these classes, you can define your loss function just simply as the sum over the different classes over here, and then in your output layer you just need a sigmoid function, and that's also fine, which gives you a value between 0 and 1. And this is what we used in this particular case of our classification neural network. And now maybe coming back to your question, so the information that you get is that for every atom I over here, you get a value y for each of these p classes that we have. So every atom over here has a vector associated with it that has 5 entry values. And so, for example, what I did here in these different snapshots is I colored the atoms according to their value yi over here for the different classes. So in this case, I colored all the atoms according to their value of yi here with respect to BCC. Does that answer your question? Okay, perfect. Output classes that you have, and so here the atoms are colored according to the output for their BCC class. Here they are colored according to the output for the disordered class. Here for the A15, and here for FCC and HCP, which is essentially all 0 in the system. And you can see this works very nicely, and the classification accuracy is very, very high in this type of approach that we've chosen here. And the other thing that you can see is that now, of course, if you want to describe the whole system, and now the information that we have at this point is very local, what you can do is a global classifier. In this case, what we did is something very simple. We just took the average of these local classification vectors over here. You end up with these global classifiers, which essentially gives you the phase fraction in the system. And so here you can see we have about 20% BCC in the system. We have about almost 30% of nothing of our HCP and FCC in the system. And so now we're using these global classifiers, and you can already say, okay, that's already great. Maybe you just use these global classifiers, and then you can just use your enhanced sampling technique in the space of global classifiers. Well, the problem is if you're looking again at something like a phase transformation over here, you can immediately see that all of these global classifiers are not independent, right? You cannot form more BCC if you're not reducing any of the other classes in the system. And because they are not independent from each other, when we're trying to do that, it didn't work very well. So what we did instead is that, again, we did, on top of all of this, a nonlinear combination of our global classifiers over here in what is called a path collective variable in the space of classifiers. So the path collective variable is defined like this, and graphically you can think about it in the following. So if we have our two-dimensional space now of these two global classifiers, we can define a path in this space of the classifiers that goes from a little bit of BCC and a lot of A15 to a little bit of A15 and a lot of BCC. So essentially from here to here. So this path brings you, this point is this structure over here, this point is this structure over here, and this path, in this sense, if you just think about the phase boundary moving in this direction, you just have more and more BCC and less A15. It's just a linear path in this global classifier space. And now your path collective variable is now a one-dimensional object that changes from 0 to 1 along the path. And it's constant perpendicular to the path, and it increases from 0 to 1 along the path that you have. And this is now essentially the collective variable that we then used in our enhanced sampling approach. And our preferred enhanced sampling approach that we are using here is called driven adiabatic free energy dynamics, which is an extended Hamiltonian approach. And what you have here is you have your regular Hamiltonian. So this is the momenta kinetic energy of your regular system. This is the potential energy of your regular system. And then you also have the momenta of your extended variables. And you have a coupling term over here that couples your extended variables to the collective variables. So now my Q over here, that's my collective variable. In this case, my past collective variable that I'm interested in. And this S over here is my extended variable, which is an additional variable in my extended Hamiltonian that I can then drive to explore the energy landscape in my collective variable space. And the trick that you do in driven adiabatic free energy dynamics is that you choose the mass of your extended variable to be much, much larger than the effective mass of your collective variable. And if you do that, then you get an adiabatic coupling between the two systems, and you can recover the free energy of your real system at your real temperature, even though you're running your extended variable at a much, much higher temperature than your real system. So you can think about it as the following. If you think about now your energy landscape in your collective variable space, then you have your extended variable, which is a very heavy but very heavy particle that runs at a very, very high temperature. So it's kind of like slowly exploring this energy landscape, and because of the high temperature, it can actually overcome these higher barriers much more easily. And then you have your real system, which is much lighter and which kind of like vibrates around it. And it's kind of like being pulled along with your extended variable. No? And so then you get trajectories like this. And of course, in this case, the dynamics, they are not really realistic anymore. But what you can see in this particular case, so this is now the value of our path collective variable. This is the time in our enhanced sampling simulation over here. And what you can see is that you sort of like get these sort of plateau regions all over the place. So somehow, if you're moving the phase boundary, some sort of like stochastic process over here, which still has these plateau regions over here, to move the system all the way from just being mainly A15 to being mainly BCC in our system. This time over here is still a lot faster than if you were running this at the regular temperature of the system. So if you try to sample this transformation without any enhanced sampling, then this will take several microseconds or hundreds of microseconds for this process actually to proceed. So we can get a much, much faster exploration of our phase space if we're using this one-dimensional path collective variable together with our driven adiabatic free energy dynamics in our system. And we can see that we somehow, we sort of like have a structure in here that kind of like tells us something about how this phase boundary here moves. And if you analyze these different plateau regions, then you can see that's essentially whenever the system sort of like moves and creates like a whole new layer of your body-centered cubic phase in this particular case. Yeah.
So you always start with the phase boundary present. So it's
yeah.
more about the movement of
yeah.
the phase boundary, not the creation.
Yeah. So in this particular case, so we wanted to get it all the way to the nucleation, but already in this case, already the motion of the phase boundary itself is a rare event. Yeah. And so the type of energy landscape that you then get, so here we can extract then, of course, from all our simulations, we can, for example, extract the potential of mean force for our system. And this is now an energy profile along our extended variable that we get in the system. And what you can again see is this kind of like layer by layer transformation with these barriers in between that are about like more or less like half an electron volts. We can't use anything here and anything here because we have constrained this other interface over here, so the data here are not very representative. But in the middle, we can see this layer by layer transformation with an energy barrier of about half an electron volt, which is actually very nice because this barrier that we see from our potential of mean force is also consistent was an effective barrier that we got in an earlier study where we used adaptive kinetic Monte Carlo to sample this transformation, and also some high temperature molecular dynamics, and we did an Arrhenius plot, and also we got a similar barrier in this particular case over here. So actually, which means that the potential of mean force that we get along our slightly complicated collective variable actually makes sense in terms that it recovers an effective barrier that we've seen before also from other simulations. Now the question is, why should that actually work, and why do the forces that we get from this very, let's say, more or less complicated way of getting our reaction coordinate, why does that actually give us the right answer over here? So the forces, the extra forces that we get on our system to do the enhanced sampling, they only come from the coupling term, right? So we said we couple, in this case, our path CV over here with the extended variable over here, right? So this is the coupling term. So now, of course, the coupling force that we have on our atoms over here is then, of course, just the derivative of this coupling term, this coupling potential, with respect to our coordinates, which essentially is the derivative of our path collective variable with respect to each of these coordinates, because this is the same for each of our atoms, of course. Now, if you remember, what we did here is that we have our coordinates, we plug them into our descriptors as input to our classification neural network. This gives us an output of our classification neural network. This we kind of like combine into these global classifiers. This we plug into our path collective variable, and all of this we can do all the derivatives here in a very long chain rule thing, of course. And if we look at those forces, then we can see that really those coupling forces, they are large at the interface, and they're very small whenever I'm in like a perfect bulk region. And the reason for that, and the reason why that works, is that if you look at this, if you look at a classification neural network, and if you look at the derivative of the output with respect to the input features over here, then so essentially what you're training here is, of course, a decision function, right? So if you are in two dimensions, we have our decision function over here, and then we have the decision boundary between our two classes over here. And whenever I'm very much inside my decision region in one of my classes, then these partial derivatives, they are very close to zero. They're very, very small. And those partial derivatives, they only have a significant contribution whenever I'm close to the decision boundary between two classes. And that's exactly what we want. So we wanted to have it like this, but actually we can the interface where our atoms are sort of like in between the different phases, we actually get these additional forces that are very large because we're close to our decision boundary. And this, with our classification neural network, we're trying to push the atoms either into being a perfect BCC or into being a perfect A15 in the system. And that's why this actually works in our system. How much time do I have?
5 more minutes will be okay?
Yeah, that's perfect.
Yi is something which is computed atom by atom, right?
Yes.
So then dy over dg alpha is probably large, but it's also fluctuating a lot. Is my intuition correct?
Does it fluctuate a lot? You mean depending on if you're pushing this around in your classification space?
Yeah, I guess from one atom to the table, or from one classification to the next one.
It doesn't seem to be. So we didn't see any, let's say, numerical problems or numerical instabilities with that. We have not analyzed that in that much detail, I have to admit. So we were looking at, we essentially what we did is that we looked at a couple of these snapshots, or we essentially made a movie, and then we were looking at just coloring this by the forces that we get, which seemed okay. It didn't seem too erratic, but we haven't analyzed it in that much detail. Might be interesting to check that. Yeah. So the last couple of minutes, I'm just gonna use this as a little bit of an outlook of what we are trying to do with this now to apply to other systems. Of course, you have polymorphic transitions in all kinds of other systems. In particular, what we're trying to do now with the people in New York to look at these transformations in molecular crystals, which has all the same problems that I was discussing before. You have nucleation and growth, you have interface migration, you want to know what happens if I put in defect seeds and stacking faults and whatever. The problem is that now, on top of just having a lattice to worry about, you also have to worry about the position and orientation of your molecules in the system. And so that comes in when you try to do a suitable feature selection to capture the local environment in the molecular crystal. So everything else, let's say all the rest of the framework, that can be pretty much the same, but selecting the input features, that has to be slightly different if you're using something like a molecular crystal. Because also if you think about a polymorphic transition in a molecular crystal, now urea is very simple, but in general, you not only have, let's say, a rearrangement of the positions on the lattice, but usually you also have, let's say, conformational changes in the molecule, right? So to be able to classify and to be able to drive the transformation through these local changes, you also need to be able to drive conformational changes in these systems. So for now, what we said, okay, what we're trying to do is using this point vector representation still together with the symmetry functions, which, again, in the case of urea is very simple. In this case, you can let's say, define the position of your molecule just based on the position of one of your atoms. And you can define the relative orientation of two molecules by these two vectors over here. So one is the vector from the carbon to the oxygen, and one is the vector between the two nitrogen atoms. So this gives you the possibility. So this one here gives you the possibility to say, oh, are my molecules like this or like that? And this one here gives you the possibility to say, oh, are they like this or like that in the system? And then you can use this sort of representation and again put this in some sort of like input or create your input features using this together with the symmetry function that I discussed before in our system. And just as a little bit of an outlook to show you that actually works, at least for urea it works, and we tried it for one other system which almost worked, not entirely yet. But this is an interface between two phases in urea 1 and urea 4 over here. And again, in this case, the molecules are colored according to the output of the classification neural network. And again, you can see that the classification neural network can clearly distinguish between molecules that are in a urea 1 environment and molecules that are in a urea 4 environment for the system. And then, of course, we can use this again to construct our past collective variable, use that in enhanced sampling, and then also try to drive structural transformations between different polymorphs in these molecular crystals. And so just to summarize, what I was talking about today is essentially that we would like to use the decision function in our classification problem over here to drive the system between different states that we have. And in particular, here we were looking at structural transformations, and if we're using this local classification over here, we can drive these structural transformations through changes in local structural motifs that we can enhance by using, or that we can promote by using enhanced sampling techniques in our system. And with that, I would like to thank my collaborators at NYU in particular, who we've been working with on the polymorphic transition. Of course, we are always grateful for funding from the different funding agencies. And thank you very much for your attention.
Thank you, Jutta. Questions? Yes, Marilou.
Thanks, Jutta, for the really nice talk. So I was wondering how much does, of course, the driving path you have thanks to the classifier relate with a physical path, and maybe how much does it matter if it does not?
So from what we've seen, let's say, in comparison to some high temperature MD, that it actually does give you a fairly good impression of the physical path. I think the reason for that is that you are, I mean, if you're doing the enhanced sampling, you kind of like just kind of like nudging the system. And what we are doing here in terms of these local motifs is that we say, okay, here's something should, in this region, you should make a transformation. But that's of course always the danger if you use a biasing technique, that you might bias the system into something weird. And that was our hope with using this these local structural motifs, where we say, okay, the transformation, so it has to proceed by changes in these local motifs. So if we enhance structural transformations of these, or transformations in these structural motifs, that will hopefully give us a good picture. Let's say like this. So it's not it's not a completely agnostic way of constructing this. Yeah.
Can you please go on slide 24? So the structures in the middle and the right picture on the top and bottom seem to be the same, just there is transition region between them. Are they supposed to be different, or are they the same? Just there is some.
They're different. So these are two different polymorphs of UVM. So if you look at this, so well, you can see it like a little bit in terms of,
Yeah,
if you
here
look at
I see that they're different, but
yeah, this is the same. This is the same. Like all of these things, it's the same snapshot. There's no. This is the coordinate, the atomic coordinations of these different in these three pictures are exactly the same.
Okay, thank you.
Hi, Peter.
Yeah, I probably missed half of your talk, but
That's
it's all right. So in the last application of the transition from BCC to AB13, I think.
Weird, yeah.
You showed the free energy, which looks actually quite flat in overall between the overall states. But if you look at your biased trajectories, if you go one slide back here, you always see it going in the forward direction, and S going up. Can you explain why it's always going in the forward direction and never changes back?
I did not put this slide. So in this case, we only sampled. So in this case, we always started over here, and we only sampled in one direction. We also did it. So in this particular setup, depending on the lattice mismatch and whatever you're doing to the system, BCC is more stable than A15. If you're sampling this back and forth, what you would get is a tilted energy landscape. And we also did that, huh? Because we only did the forward sampling. So it's only an estimate of the forward process. We never did backwards. Not if you never go back, right? So then you always just go forward, and then you go forward. You never go back. You only get the forward process in this respect.
Okay, maybe we should discuss.
Yeah. So we did it. Yeah, no. So and you do. So if you properly sample the forward and backward transition, you get an energy landscape that has exactly this one here, and it has the forward barrier, and the backward barrier is this forward barrier plus the energy difference between A15 and BCC. And it looks like this. So if you have your, if this is your pass CV over here, and this is your energy, then it looks like this.
Yes.
Yeah.
Okay, but then I'm confused, because what is the right picture then? I mean,
No. So this is only if you're just doing this once. So if you were doing this, let's say, for example, with metadynamics, right? So if you do the first pass, you get this, because it always just goes in one direction, and then you keep sampling here, and then you go back a little bit, and then it gets more tilted and tilted as you go along.
So what you showed is only the first part.
Yeah. So what we showed is essentially only the first part and the first path. It does, and we did that.
Okay.
And we did that. So in the paper, we also have the forward-backward thing with metadynamics. Yeah.
Thank you. Any more questions? Yes, please.
So you mentioned nucleation, and so I would like to know more if you have idea how to apply this to the case of nucleation, and related also to what when you said why does it work. So it looks like indeed that it's, if the let's say reaction coordinate it's somehow local but complicated, this is what you can catch. But whether once you start to be, for example, if I think I have just in one phase and have to nucleate a bubble, of course you can, I mean, it's with this nonlinear transformation, you know where the interface is, but instead of having, I think, a sequence of, let's say, local transformation, you have to go on top of the barrier. So it means that you have to have a lot of improbable events, one after the other. I don't know if maybe I'm not clear, but what I mean is that once you have the interface that is there, you know how, I mean, to move it, what are the, let's say, non-local transformation that you have to do. But you can do it one here, and then one here. I mean, it's not, to go on top of the barrier, you don't have to do all of them one after the other. So it looks like when you have to do, you have an extended move in space to do, then it might be much more complicated. Did I get
it might be more complicated. So for nucleation, so we haven't tried it for nucleation yet to see how that goes, because essentially you need to, you somehow need to start somewhere, right? So that's maybe what you mean. If you have like a homogeneous, or if you just have one phase, you can do like a nucleation event over here, over here, over here, and you're not really sure. So that the system would have to start somewhere to continue biasing at the same position. Is that what you mean?
Yes, and then it has to continue. I mean, it's even if you have the, let's say, the right coordinate for the interface, still you have to create an interface which is large enough.
Yeah.
That is growing. So creating large enough, it's still a great process.
Yeah. So I'm not. So it's not. You don't have to have the whole interface, right? So that doesn't really matter. So a small system and it's periodic and all these different things. But you could also think about let's say, a spherical nucleus, and that's fine because you still have an interface, and it doesn't really matter, and it will drive the system in all different directions, and that should not be a problem in that sense, because the point is that, of course, in the enhanced sampling, that's what that's the whole point of driving the system up a barrier, right? So you can do it with the DFAT, but you can also do it with metadynamics. In that sense, you would just build it up, and you would eventually come to the barrier that you're interested in, right? But if you don't have anything, so for initial nucleation, I'm not entirely sure if that works or how well that works. We haven't tried it in that context yet. Yeah.
Okay, thank you again for a nice talk. So we now take a 20 minutes pause, please. Thank you. set eBay on a deep learning based algorithm for solving PD eigenvalue problems. Thank you, Wei.
Thanks. Everyone, I'm very glad to be here to give this talk. Actually, I have given this talk on similar topic before, but hopefully this one I have some new stuff and to show you. I work at TUS Institute Berlin, and this is a joint work with. No, the point don't work. Okay. Yeah, this is a joint work with Tiejun Li from Beijing and Christoph Schutter from Berlin. Yeah, this is the outline of my talk. I will, first of all, give you some effective dynamics. And this is related to what this explains why I consider this eigenvalue problem. And I show you deep some numerical examples. Then I discuss a little bit related to the methods. So the first part, actually, the molecular dynamic simulations. I believe we have already heard a lot from we are interested in some conformation or material science. Here I focus on system from biophysics. And this is a picture I took from this paper. You can see that for each row, it displays the different conformations of one small protein system. For example, the first row shows that there are actually different conformations, metastable conformations of chinolene. The system can stay in a folded conformation, and it can unfold to another state. And understanding the transitions from one state to another is typically a rare event. And this poses a challenge to the standard MD simulation method, and then many people are working on this. So the key questions for this related there are many key questions. Two of them are the following. So the first one is that we want to identify stay in some conformation and stay there for a long time before how and how often do the conformation change. So basically, along which transition pathway does how often it happens. So these are the typical questions. And to answer these questions, also relate to other questions, there are consider different quantities. So people studied, for example, minimal energy paths to characterize the transition pathway. And people studied commuter functions, passage times, and low-lying eigenvalues, eigenfunctions, and also quasi-stationary distributions. So all these quantities can give us some information about the mechanism of the dynamics of the underlying systems. On the theoretical side, people can work with large division principles to characterize, for example, the minimal energy path or minimal action path. Statistical framework, transition path theory, quantities, for example, reaction rate, flux, the dynamics. There are also some others. On the algorithmics side, people studied surrogate modeling, for example, the system is typically we want to do to reduce the system's dimension, and this also want to overcome the difficulties in sampling, and for this, many enhancement sampling methods have been developed, and also people directly simulate the transition pathways using transition path sampling, or the most dominant ones by stream method or NEB method like that. And people also can build Markov state models to understand the transition mechanism. So in words, so there are many works in the past, I don't know, 2 or 3 decades, and so the eigenvalues and eigenfunctions, and I show you how this is related to the effective dynamics, and I will provide a way to solve these eigenfunctions. For the systems, I make so-called underdamped long-run dynamics, which is given by equation 1, dx equals minus gradient v plus the noise term dw, rescaled by some parameters, beta, which is related to the strength of the noise. For empty systems, the dimension is simply the 3 times number of atoms. So here, in these systems, the beta is related to the inverse of the temperature, T. Then to study in 1 instead of the long-term dynamics is really the by equation 1. For example, is the Boltzmann. The infinite very important. Satisfy the equation 2, which basically say that L weighted inner product mu, and if you apply L minus L another function G, it's equivalent to first act L on G and then take inner product to F. So basically you can switch the order to test the function, and you actually have so here L contains second order derivative Laplacian. You can change it to a form which only has the gradient of the function. So the second order disappear, especially if you choose Fn equals G, and then the right hand side of this equality actually give you the energy of this so-called the Dirichlet form of the generator. So I will actually, so you need a condition on the potential V to make everything rigorous. And explicit conditions on the potential V can be by this paper by 2016. And more generally, dynamics, but I will discuss a little bit about the more general dynamics. To apply the algorithm in this talk to transfer operators. So this is the effective dynamics, which actually reduce the high dimensional dynamics to a low dimensional one. And I will mention how the time scales of this effective dynamics is related to the original one, and why eigenfunctions of the original dynamics appears, how eigenfunctions appear in this setting. This is so this figure actually shows that people have developed different surrogate models in order to study the original molecular systems, which is assumed to be a very high-dimensional space. So, for example, you can cross-screen your atoms, mass centers, and this will give you some cross-screened model. But here in this talk, I will be more interested in a model which try to characterize the dynamics information, not the configuration representation of the configuration, but the representation of the dynamics. And so in this part, people actually can consider, for example, you want your model, surrogate model, to be discrete in time, then you can use Koopman models. You can build Markov state modeling. Maybe you also want to have a continuous time models, basically effect. If you are satisfied with the Markovian dynamics, you end up with the dynamics I will discuss in this talk. But you can also include memory to get a generalized Langevin equation. So here, previous talks. So here the setting is the same, but I will work with a nonlinear map from high-dimensional space to a low-dimensional one. So the reason to work with map is that in many cases, people have a high-dimensional dynamics we want to understand, but in many cases, you are only interested in how the apply in Ito formula in probability theory to get this equation 3 for the evolution of the collective variable under the original dynamics XS. So XS is in high-dimensional space. You map it to a low-dimensional one. Actually, you can write down the equation for this dynamics. This dynamics is not a dynamics of the low-dimensional object itself. The information of the four dynamics. This can be seen on the right-hand side of the coefficient. So the idea proposed, for example, by Legault and Livier, is that we want to construct a dynamics, effective dynamics, which replace the coefficient in this one by some averages, such that we obtain a truly low-dimensional SD, which is Markovian. So the idea is that you replace the coefficient, the true one, by the mean value. And here I show that so the mean value is taken with respect to this so-called conditional mirror on the level set. So given a value of the Cassi, here we assume that the Cassi is, you choose a Cassi already known. And for each value Cassi, you can look at the level set. And this mirror is simply the Boltzmann distribution constraint on the level set. You compute your coefficient, the mean value of the coefficient with respect to this mirror, and you you use it in the SD, and you get a SD of the effective dynamics. So basically, I will not go to more details about this one, but tell you that there are some works since this dynamics has been proposed. For example, the question people want to ask is that how close is the effective dynamics compared to the true one? So by the true one, I mean that the evolution of the Cassi under the true dynamics. So this true one is not Markovian, and we build the effective dynamics. Markovian effective dynamics, we want to understand how much we can believe this dynamics. And for this, you have different notion of closeness of the two dynamics. For example, you can ask what about the timescales? If I want to understand the timescales of the original dynamics, how the timescales are preserved by the surrogate models. You can also look at, in more detail, pathwise, you can compare the path of your true one and the effective dynamics. You can also look at some entropy estimate. Basically, you compare the distribution, the probability marginal distribution, for example, of the two dynamics. In this talk, I will only as a motivation of the eigenfunctions, I will only discuss the timescale approximation. So the idea is that the question I want to ask is how close are timescales of the effective dynamics to the true timescales. So for this is how the eigenfunctions enters in this picture. So actually the timescales of the original dynamics is characterized by the equation 5. So here, this is a eigenvalue PD problem associated to the generator L of the original dynamics. Once we can assume that we can solve this eigenvalue PD problem, then the eigenvalues lambda 1, lambda 2 will give you actually determine the timescales of the original dynamics. So the question above actually becomes that how close are the solutions, the eigenvalues to 5 and the eigenvalues to the problem 6. For equation 6, basically what I changed is that I replaced the generator of the original dynamics by the generator of the effective dynamics I just showed you. Actually, this is the result we got several years ago. So this result basically say that you can compare the eigenvalues, and this lambda tilde is the eigenvalue of the effective dynamics. It is always bounded from below by the true eigenvalues. In another word, we always overestimate the eigenvalues, or in other words, the timescales of the effective dynamics become faster. So basically, you can think about that. We actually do some cross-graining, and the energy surface becomes smooth. The timescale becomes faster. So that's one way to understand this result. You can also the error actually depends on how well your eigenfunctions can be represented by the eigenfunction of the effective dynamics. The difference actually tells you the error of the eigenvalues. Why eigenfunctions are important? The reason is that, as here I state here, if you choose Cassi, the 7 actually is true for any Cassi. If I choose Cassi in particular to be the first eigenfunctions of the original dynamics, actually you make no errors. So basically, you choose this particular Cassi, you construct the effective dynamics, and the timescales actually are preserved accurately. So this is why the eigenfunctions are interesting to me. So far, I always focus on the timescale defined by the full dynamics. Basically, I didn't specify the domains or the two sets A and B as in transition path theory, but actually you can do the same things. For example, suppose we are interested in some exit event from a domain D. Then in this case, the particular function will be the quasi-stationary distribution, no longer the eigenfunctions. If you are interested in transition event from one set A to another set B, and you apply the framework of the TPT framework, then in this case, the commuter function is really the function to look at. So the conclusion I want to make is that I would like to say that the collective variables eigenfunctions are in some sense optimal collective variables, but it really depends on the problem you consider. With this motivations, now I focus on the eigenvalue PD problem. And in this part, I will show you a training algorithm to solve these eigenvalue PDs. And so for this, actually the idea is very simple. We want to train the neural networks according to some loss functions. So the first step is to find a loss to train the eigenfunction. Actually, in my case, the loss comes from the variational principles. So basically, we want to reformulate equation 8 by some variational principles. So let's look at the first eigenvalues. Actually, this is well known, I believe, to many of us. If we want to compute the first eigenpairs, lambda 1, phi 1, to the equation 8, it is well known because this is well known that if you consider this quantity, this is the energy gradient of f, square root of the gradient of f, and you take expectation with respect to the invariant measure, then the eigenfunctions is the minimizer of this functional among all the normalized function. So here. And the eigenvalue is simply the value, the energy of this eigenfunction. So this is widely used, for example, in quantum mechanics. So the point I want to make is that actually this result can be extended to multiple eigenpairs, because in the end we want to compute not only the first one, non-trivial eigenfunction, but the first several, because there might be several eigenfunctions that we are interested in, and that can characterize the dynamics, slow dynamics of the system. So the extension, actually, the idea of extension is very simple. So basically, instead of looking at the energy, now I look at, instead of looking at the energy of one function, now I look at energy of several functions. But to have a scalar, I do this linear combination. And I compute the sum of omega I and the energy of function fi. Omega are some constant parameters I need to choose. And this result tells us that if you look at this energy among all the functions orthogonal to each other, so under this constraint 11, you minimize this energy, then the minimum is achieved when the function f are the eigenfunctions. So, and this actually gives us a natural loss function to use to train the neural networks. So to summarize, this will be the optimization problem that we will focus on now. The idea is very simple. We want to construct k neural networks, and each represent one eigenfunctions, and we design loss functions based on the optimization problem 12. The problem is that this function, this optimization problem is constraint optimization problem. We have to deal with the orthogonality constraint between two pairs of functions. And we also have to make sure that the function has mean values. The point is, the observation here is that actually the mean value constraint is not essential. We actually can handle it after the training. So we consider function fi, and replace the second orthogonality constraint by the covariance constraint between the two functions. And here is the definition of the covariance. And you train the neural networks. And in the end, the function neural network will not satisfy the first constraint, but this can be simply done by recovering, by shifting the mean value of the function. And then in this case, both constraints in equation 3 are satisfied. And we also need to handle the integrals in the optimization objectives. So the expectation appeared in the objective function actually are high-dimensional integrals. The standard way is to replace the integrals by some Monte Carlo samplings. Here, the idea is that you can actually do important sampling and collect data from another distribution, mu bar, and write down a weighted estimator of the mean value in the loss function. And this will allow us to train the neural networks from distribution, from sampling data and using biased dynamics. So the idea is that I have a constraint optimization here, and I replace the constraint in above by some penalty terms. And this will be my loss function in the end, used to train the neural networks. Basically, the idea is that you have to satisfy that constraint. And in the previous slide, I showed that this is equivalent to imposing that covariance between two functions equals delta. And the penalty here is that I simply want to impose this value to be 0, so I square it and put it in the loss function with a large parameter alpha. And the first part actually is a modification of the energy there. So this is the Rayleigh quotient. There is the energy. This actually is really for numerical purpose. You can use the original one as well. Now I show you some examples I did so far. The first example is a toy example. The idea is that I want to verify the algorithm using a high-dimensional system where the solution can be computed by traditional PD method. So the idea is that I start from a two-dimensional potential. I extend it to high-dimensional one by adding several Gaussian potentials in the remaining dimension. So because the Gaussian potential and although that I modify the potential, but the dominant eigenvalues and eigenfunctions remain similar, close to the two-dimensional potential. So that's the idea. So basically, this is a problem I compute. I have a generator L, and I solve the problem in different dimensions, 2, 50, and 100. And I need to sample some data, and I compute the first 3 eigenfunctions. And this is my neural network architecture, and other things are standard. So this is the data I get. You see that in each dimension, actually, the data actually sampled well the 3 different wells. There are 2 wells, A and B, and 1 shallow well connecting these 2 deep wells. This is the result of the training procedure. We can see that it converges relatively quickly, and each eigenvalue also converge. This picture tells us that actually also the constraints are preserved during the training process. Most of the time, the training is between 10 to minus 2 and 10 to minus 3. So basically indicating that the 3 eigenfunctions indeed satisfy the orthogonality constraints. And so here, as I said, that in this case, I can compute using finite volume method the first 3 eigenvalues. This is really comes from the finite volume method. This is the method I obtained by training neural networks. And you can see that they actually approximate the traditional method quite well. This is the eigenfunctions. Again, the first column is the solution obtained in 2D using finite volume method. And in other columns are the solutions of the neural networks. For high-dimensional problem, what I did here is that I have the eigenfunction is essentially a high-dimensional eigenfunction. So I randomly choose values of the dimension x3 to xd, and I project onto the first 2 dimensions. You see that they actually are very close to each other. As a test of the molecular systems, I studied the simplest one, alanine dipeptide, in vacuum. So the problem now is this one, also appeared in the previous talks. It has 22 atoms, and the total dimension is 66. So in this case, I cannot do straightforward simulation. I have to do some important sampling. Here I use adaptive biasing force method to get this sample, so such that the configuration space is well sampled. This is the training data I use. And maybe I mention one thing is that for this problem, I have to what I want is that I want to compute the eigenfunction, and I know that the eigenfunction should be invariant under translation and rotation. So the idea is that, similar to the previous talk, I have to do some trick in the input layer. What I use in the input layer is that I use all the coordinates of the non-hydrogen atoms. So there are 10 non-hydrogen atoms. So the dimension of the input layer is 3 times 10, 30. But after this layer, I have to impose this translation and rotation invariance, what I do is that I use this map. Basically, there is no training parameter in this layer. What I do is that I compute, you give me an input x, I compute the optimal translation and optimal rotation matrix using the algorithm called the Klaprosch-Messer algorithm. And this actually defines the map. And with this map, the function is guaranteed to be invariant under translation and rotation. So these are the training parameters. Here I compute the first two eigenfunctions. This is the solution. The first row is the solution of the first eigenfunction computed on the training data and on the validation data. And similarly, you can see that the eigenfunction really give you some information about the metastable set. For example, all this part is colored by blue, and this part is colored by red. And similarly, this function, if you look at the sign of the function, you recognize that the difference is actually this part and this part, because you see red here is positive, blue is negative. So really this function, the second function, give you the information about, sorry?
Okay, so this is in vacuum?
Yes.
And then, just so I understand the workflow. So if it wasn't, you might first learn an effective diffusion coefficient and then apply the same scheme?
Yes, so I probably will discuss a little bit more, but you are right. So this is in vacuum. Basically, what I compute is that I have a generator, and I compute the eigenfunction for this generator. Right. So if your data comes from another dynamics, this is slightly different. I have to do some, this will be discussed later. Yes, so the idea is that the conclusion is that the eigenfunctions give us some information about the metastable set. So finally, actually, I got some questions from Pierre last time I give this talk, and people ask what is the difference with the method based for transfer operators. So the idea is that let me first summarize what I did so far. So the algorithm of my talk actually compute eigenpairs for a specific generator. So this means that I have a SD set at the beginning, which is the overdamped Langevin dynamics, given potential V. And for the training, I do not require time-lagged data. So if I go back to my slide here, so here you see what I do is this one. So there, I don't need, you don't see the lag time tau. All I need is that I need a data set which sample the invariant distribution. It doesn't have to be a time series. It can be some data coming from Monte Carlo method, for example. You don't need time informations. So why this is possible? I mean, especially for people who are familiar with transfer operator. So this slide is try to explain my current understanding on this difference. So the algorithm I presented so far is for this specific problem. I compute the eigenvalue problem, and you can use different data to feed in this training task, and you don't have time-lagged data. This is not necessary. But then for transfer operator approach, what people actually do to start with is that there you assume that the dynamics is described not by SD, because they want to be data-driven method. So the idea is that you have dynamics described by a density here, p tau t, given x at y. So this is the probability density given x at time t, and you look at the density of the state at t plus time tau. So in order to continue to make this approach work, people make two conditions, basically. The first one is that you have to assume that your tau is chosen properly such that the density becomes Markovian. And the second one is that you also need that this is a reversible, it defines a reversible Markov chain, and it is ergodic. So then you can define the transfer operator in this way using the p tau. Now there is no time-dependent t. And this is a Markovian kernel. You can define the operator which is called transfer operator. The key point is that the transfer operator satisfies similar to the generator, and it satisfies this self-adjoint equation. So the question is, first question is, what is the connection between what I'm doing and to the transfer operator? So we actually, what we can say is that, again, assume that the dynamics satisfy SDE of the form I start with. Then in this case, you know that the transfer operator is related to the generator in this form. So especially transfer operator basically is a semigroup defined by the generator. But in general, the advantage of the transfer operator is that you don't assume that where the data comes from. So it can be some long-term dynamics or a system with some solvent. You look at not the original data, but the data first projected in some low-dimensional space by features or by removing the hydrogens, and you can still apply the transfer operator. But the problem, the approach I present in this talk so far has to be changed. So the idea is that whether this is possible, this is slide try to say that this is still possible. So the only thing we use to design this loss function is basically the variational principle, and this variational principle actually only requires that the operator satisfy this self-adjointness, and whether it is generator or transfer operator, it doesn't that much. So the same thing is, so using this fact, actually for transfer operator, it satisfies the same thing there. The only difference is that you don't have this energy. But still, what you can do is that you can simply replace the objective used in the algorithm for generator by this quantity. You look at this quantity, and you write down a data empirical version of this quantity using a data. But now the data has to be coming from a time series because you want to evaluate p tau. So you have to make sure that the data now comes from the time series. But the advantage is that you don't need, this can be applied to more general dynamical systems. So especially this loss function actually is quite close to the approach you called state-free reversible WAMP-net. So in this method, what they do is that they compute not the eigenfunction, but the basis which can represent the eigenfunction. So in other words, they don't treat the penalty directly, but they assume that they compute they train the neural network to learn a basis, and then based on this basis, they solve a matrix problem to find the eigenfunctions, and they can figure out a way to do the auto differentiations in order to train the neural network. That's a difference between these two. So now this is the last slide. So basically, this is nothing. There are several work can be done. For example, I only consider the simplest MD systems, and there are also questions that you want to adaptively do this, solve this chicken and egg problem. Basically, I assume that you have a collective variable in order to solve the eigenvalue PD problem. But more general case is that you don't have this problem. You want to actually learn the collective variable. How do you do it automatically? So I have to combine the sampling and the training together. This is what I show here. And this, sorry, that's all. Thank you.
So are there questions in the audience? Yes, Jutta.
I just have a question. One thing that I didn't fully get. So are you, when you're solving or when you're training your neural network, are you assuming a specific dimension for your low dimensional space, or does it come out of everything?
I
missed that.
Yes, so in principle, here I actually fix the number of k, which is the number of eigenvalues and eigenfunctions. But what I should do is that I compute, for example, I choose 2, k equals 2. I compute 2 of these eigenfunctions. I look at whether I should also do the same calculation for k equals 3. And I look at compare the eigenvalues get and to search for the gap. So basically, I should optimize the number of k in principle.
You would have to train, like with every dimension, you have to retrain.
Every dimension. So for I get the 2 numbers together by one single training.
Yes,
so
but if you are.
But I have to optimize k. That's But another way that you can.
But k, so that's the number of your outputs.
K is the number of basically where is so here is a k. I have to choose k and solve the optimization problem. And this solving this one will give me k neural networks. And in principle, what I can do is that I start from a large k and solve it once and search the gap.
And is that like, can you also get different? Would you always get the same, or do you get slightly different?
Yeah, so the question is that, for example, you see the eigenvalue. There is a issue here, which is sorry, I should stay here. Yeah, so I take the linear combination as my objective. So in principle, I would expect the algorithm work well if your the energy each eigenfunction contributes proportionally. For example, if you choose k to be very large, then you will have difficulties because some eigenfunction will dominate. Yeah.
Okay. Thank you.
You're welcome.
I have a question which is somehow related. So, at some point you said that for each function fi, you have a separate neural network, while you could have a unique network which outputs all those guys. And then inside the neural network, you could have some features which are used by different functions. And it's related to that because if you want to increase k to check if k was good, maybe you could do that instead of starting again with a whole new blank neural network and start again the optimization. You could try and be greedy and say, okay, my initial situation is the k first guy have already been optimized, and I start with a blank guy. But now, depending on this structure of is there a unique neural network for everybody, or are they completely separate, could have an impact.
I haven't tried that, but I think it's possible. I mean, basically here, what I did here is that for each neural network, basically the 2 eigenfunctions are represented by 2 separate neural networks. But as you said, I can actually use one simple neural network, which maps from input layer to k dimension. That's also possible. And then they will share many weights and biases. But I haven't tried it. But I think it's possible. Yeah.
I have, yeah, all right. I have 2 small questions, actually. So first, out of curiosity, how good are your estimates of the eigenvalue for the alanine dipeptide? Are they the same as your brute force calculations?
I haven't tried brute force, actually. So I have 2 examples. I only have estimation of the reference solution in this case. So this is the reason I study this problem. In this case, I can compute the solution by finite volume method.
I see.
I solve the 2-dimensional 2D PD problem, but in the alanine dipeptide, I don't have this I didn't try this.
Okay. And then, I mean, you showed your eigenvectors as a projection of two parameters, for example, phi and psi angles. But in general, of course, these projections are not known. And they are actually multidimensional.
Yes,
so
yes.
I think in the end, at the conclusion, you said that the interpretation of the eigenvalue might also be of interest.
Eigenvalue.
I mean, how to interpret your eigenvector
Yes, yes.
as a reaction coordinate. Can you say something about that? How you make
yes,
a dimension reduction, for example, for the eigenvector?
Oh yeah, so what I want to do, but I was not successful yet. So basically, I want to, for example, use, where is the eigenfunctions? Sorry. So for example, this one, I want to do some similar to what other people did. Basically, I want to do some important enhanced sampling using these eigenfunctions. I tried, but then I had difficulties. It seems that the reason is the eigenfunctions are really sharp. So it has a sharp interface in the transition region, and inside the metastable region, it is quite flat. So it seems that in this case, what I did is that I want to run ABF using, for example, the first eigenfunctions. Then I realized that if the state is in this conformation region, basically the reaction coordinate, the collective variable doesn't have that much because the gradient is very flat. This is the difficulty I observed, but I didn't. I should continue.
Yeah, so that's in the enhanced sampling.
Yes.
Okay, but maybe I didn't get it completely right. But if you have k dimensions, like Jutta was also asking about, then k can be also a much larger number, not? So if you go to 10 dimensions or 20 dimensions, everything becomes really difficult to project.
Sure.
And so the question is, do you need all of those? Are you sure that you need all of those dimensions to describe the effective dynamics?
Yeah, it's a good question. I mean, probably not. You are right. So basically, the question is, for example, you have if I look at the eigenvalues, there are 10 small eigenvalues, but the 10 eigenfunctions can be represented by a single function. That's also possible. In this case, it's enough to choose one.
So any of those 10 or 20 eigenfunctions is fine. Is that what you're saying?
I'm saying that although there are 10 eigenfunctions which correspond to the rare event, but all of these functions probably can be represented by a single function. Okay. For example, the simplest example is that you can build is that you consider dynamics on the circle, I mean in 2D, but all the metastable region is along the circle. So if you compute eigenfunctions, I mean the number of eigenfunctions are interested should be relevant to the number of metastable sets. But all these eigenfunctions actually are a function of radius.
I see. Okay.
So I mean it's true, but I haven't tried this large K.
Okay.
Yeah.
All right. Thanks.
Okay. So there is some people study this transition manifold. So the dimension of the transition manifold is probably different from can be smaller than the K. Yeah.
I wanted to ask regarding the machine learning parameters in the page 26. In the loss function, there is a jump around right before the 2000s epoch. Is this a behavior that happens when this training is repeated? Is that the behavior happening all the time? And if so, do you have any idea intuitively why?
So this one, right?
That one, and also the same is visible on the total loss function.
Here, right?
Yeah.
So I think I would understand that here you see during this part, right, before the transition, yes, it finds some estimation of the first third eigenvalues, but these estimations are not optimal. So you can actually further optimize the loss function by modifying lambda 3 and lambda 1. And after this one, you have a further decay of the loss function. So I think this is reasonable, right? If you look at here, so first of all, it gets a good approximation of the first eigenfunction, but the lambda 3 is not good. And if you do further optimization, actually lambda 3 have a drop, and this will actually further reduce the loss function. And for this, you have to, because of this orthogonality constraint, the eigenfunction actually changed. So you have to train it further, and then afterwards, all three converge. Then I think no change will happen afterwards.
Okay, thank you, Wei, again.
Thanks.
So now let's move to the final talk of this morning.
Yes, I have to change just singing things. Perfect.
Thank you. So the last talk will be given by Masha Cameron from the University of Maryland, and it will be about quantifying rare events with the aid of diffusion maps. Thank you, Masha.
Thank you. So this is a joint work with my student Luke Evans and Professor Pratyush Tiwari from chemistry and biochemistry, and all of us from University of Maryland, United States. So we are interested in study of rare events, especially those that happen in the context of chemical physics applications. So let's talk about very familiar example of alanine dipeptide. So if we try to model dynamics of alanine dipeptide, so most accurate modeling would be surround alanine dipeptide by water molecules and run really high dimensional dynamics.
Maria, I have to interrupt you.
Okay.
Thank you very much.
So, however, such dynamics would be too high dimensional, and the coordinates of every molecule would be not very informative to understand in what position our molecule is. So typically we do dimensional reduction. So first of all, water is replaced by Langevin dynamics. It is implicit solvent or in vacuum. And second, we also reduce dimensionality of the system by introduction of collective variables. For alanine dipeptide, often people take either 2 or 4 dihedral angles. The price of such dimensional reduction is that dynamics in collective variables becomes according to this more complicated stochastic differential equation. So I call it anisotropic overdamped Langevin dynamics or overdamped Langevin dynamics in collective variables. So in this SDE, M is a diffusion tensor and F is free energy. So this is a time reversible dynamics but anisotropic. All time reversible anisotropic dynamics are given by stochastic differential equations of this form. So now a little bit more details. So here is free energy for alanine dipeptide. And here is depiction of diffusion matrix. Diffusion matrix is 4 by 4 and projections onto various pairs of dihedral angles are displayed here. So our goal is to identify reactive channels or maximum likelihood transition paths and estimate reaction rates or expected escape times from basins of attractions. So we use the framework of transition path theory proposed by Erik van den Eyden and Weinan back in 2006. So we consider system evolving according to stochastic differential equation and mark in it 2 metastable subsets of interest, which we denote by A and B. So, and we are interested in transitions between A and B. So transition path theory studies reactive trajectories. Imagine a very long trajectory evolving in the space. We cut out of it reactive pieces. This means those that start at A and next go to B without return to A. So the main function that needs to be computed in order to apply this transition path theory is a commuter function. Commuter function of X, where X is any point in space, is interpreted as a probability that starting at X, we first reach B rather than X. This function is a solution of backward Kolmogorov equation, where L is the generator for the governing SDE. So once backward Kolmogorov equation is solved, this is the most challenging technical part, then we can straightforwardly calculate the reactive current that will show us reactive channels, and we can also straightforwardly calculate transition rate, that is the average number of transitions from A to B per unit time. So this is different from escape rate that, for example, given by eigenvalues, but they are easily convertible one to another. So here is an illustration of transition path theory on a phase potential. So in this potential, we mark 2 metastable states that are ice. This energy landscape offers a dynamical trap, which is nose and mouth on the way to A to B. If we compute the commuter function, it will look like that. Barriers here and here are comparable. Noise level is not too small. As a result, we have quite a large region where probability to go first to B rather than A is about 0.6. And reactive current is given here. Here is the magnitude of it. You see that transition current is focused along this particular channel. So this area actually is dynamical trap, so that if system goes there, it doesn't do useful progress from A to B. So now how we can compute a committer. So these are approaches that are being practiced. So first of all, finite element method. Finite element method is very reliable. There is well-established conversion theory for it. However, it is good only for low dimensions. For example, dimension 2, even in dimension 3 already you need to triangulate 3D, and there are a lot of possibilities for bad triangulations to happen. It's already a very non-trivial problem in 3D. But in 2D, it's good for comparison. Next approach is neural networks. So there are works of Kulu and Ying and Lilin and Ren, one of 2018, another one 2019. So there are also works by Rotzkopf and van den Eyden. So this approach showed that it can work in really high dimensions. For example, dimensions 100 was handled by Rotzkopf and van den Eyden. Cons that there is no convergence theory yet. It is a subject of active research, and it is not clear right now how we can control numerical errors when we use neural networks. Another approach is tensor trains. For example, there is work by Chen, Hoskin, Ku, and Lindsay, 2021. On one hand, it does work in high dimensions. They used it for discretized stochastic partial differential equation. On the other hand, when you use tensor trains, your domain needs to be box. It's often very inconvenient. Second, it is quite hard to implement, and the difficulty of implementation depends on some features of the problem. For example, for 1D discretized SPD, it is easy to implement, relatively easy, but already to extend it to 2D SPD creates difficulties in programming those tensor trains. So another approach that I am focusing in this work is diffusion maps. So originally, diffusion maps were proposed by Kaufman and Lafon as a nonlinear dimensional reduction tool. In recent works of Banish, Trutstanova, Bitraker, Kluse, and Koltai, a lot of interesting things with diffusion maps were presented. In particular, they showed how one can use diffusion map algorithm where points sampled not from the same measure as we want invariant measure for the system to be, hence it works with enhanced sampling. So pros of this approach that it does work in high dimensions, however moderately high dimensions. I will explain what can be a difficulty, but the same difficulty also will appear in all other approaches. Cons, that solution can be a bit noisy thanks to statistical error. So what are diffusion maps? The diffusion maps introduced by Kaufman and Lafon. So original idea was that we have a set of data points. We create graph using these data points by introducing some kind of proximity or kernel function between them. And we do adjustment to design the graph such that the dynamics of this graph that is given by stochastic matrix or the same generator matrix mimics the dynamics of original system. So most commonly used proximity or similarity function is a Gaussian kernel. So now we are not going to use diffusion maps for the purpose they were introduced. They were introduced as nonlinear dimensional reductional tool. We are going to use diffusion maps for approximating differential operators. So let's first think about the following fact. So we all know finite difference methods. When we use finite difference methods, what do? We take finite difference operator, and then we do Taylor expansion. And the Taylor expansion shows that it is approximately operator that we want to approximate plus some small error terms. So here I am using example of Laplacian operators. Diffusion maps can be used exactly in the same manner, but instead of finite difference operator, we use integral operator with kernel. If we Taylor expands this kernel with respect to epsilon, we will obtain the following. We will obtain our function f itself that is integrated with this kernel plus term proportional to epsilon over 2 of Laplacian of f plus smaller terms. This shows that we actually can use this integral operator to approximate differential operator, which is Laplacian operator. Tweaking kernel and doing some other adjustments, we can approximate whole families of various differential operators. So let's see, let's look at it in more details. So here is a differential operator written in the last slide, and here is normalization constant. So, but here we know that we also have a sampling density inserted here. So this is important because we approximate these integrals by Monte Carlo sums. So in numerator, Monte Carlo sum of Gaussian kernel with function f at data points divided by just sum of Gaussian kernels gives this limit as n tends to infinity. So it's same integral as in previous slide, but here is sampling density comes out. Now if we do Taylor expansion, after simple arithmetic, we obtain approximation to this differential operator. What is this differential operator? This differential operator is exactly the generator for overdamped Langevin dynamics, but for temperature twice as high as the data points come from. So it's a generator of the same dynamics, but wrong temperature. So Koifman and Lafon showed Koifman and Lafon as a result introduced renormalization parameter alpha. Alpha is a real number that allows us to modulate the influence of sampling density. So what did they do? When we have a Gaussian kernel like that, they introduced the following step. We can estimate sampling density according to this integral. In discrete case, here is the discrete counterpart, so it's straightforward operation. And then we divide the kernel on the right with sampling density to power alpha, where alpha is parameter that allows us to modulate. Of course, if alpha is 0, we do nothing. It turns out if alpha is 1, we completely remove the effect of sampling density. And if alpha equals 1/2, we exactly obtain the approximation to the generator of overdamped Langevin dynamics at right temperature. So this is the role of renormalization parameter. However, what we need to do, we need to approximate a generator not to the overdamped dynamics, but to anisotropic dynamics in collective variables, to this one. So how we go about this? So first of all, I want to note what is this diffusion tensor M. Diffusion tensor M is straightforwardly computed. A recipe for it is given in the paper of Maragliano and collaborators of 2006. And main thing is that we run restrained dynamics by biasing location to the desired location in the collective variable space by attaching a spring force with large spring constant. And then we sum along this trajectory. So this is the formula for diffusion matrix M. What is important about this is that it is not of the form JJ transposed, where J is the Jacobian of some variable change. Because as you see, it is actually sum of a lot of Jacobians. So it's not of that form. Second adjustment that we need is that we have not only dynamics in collective variables, we also cannot sample from equilibrium distribution. So here is very helpful illustration from Li, Lin, and Ren. So if you just sample data from invariant distribution, that's what you have. There is big lack of data in the transition region. If you use high temperature dynamics, still you get too many points in the regions near A and B, but under resolution in transition region. Metadynamics gives much better sampling and good coverage in the transition region. So hence, we need to do two adjustments. First adjustment is that we need to change kernel to account for anisotropy and position dependence of the dynamics. And second, we need to renormalize to use target density. So first about target density. So we took the idea from the work of Banish, Trstanova, Betraker, Klus of 2018, where they introduced target density diffusion maps. However, they used overdamped dynamics. So simple adjustment, extra term here where is M determinant to power -1/4 is added to renormalization of the diffusion kernel. As a result, this formula gives the kernel that we need. Second adjustment is that we need to use non-Gaussian kernel, but Mahalanobis kernel written here. So there is a work by Koifman and Singer of 2008, where they considered diffeomorphism from original space to another space, and their matrix M was a matrix that is JJ transpose, where J is a Jacobian for diffeomorphism. And the key feature in their proofs was ansatz written right here. So if we use Mahalanobis kernel, then using the fact that M is decomposable like that, we can show that it is in original variable space is simply Euclidean distance plus small term. So, as I mentioned, it's not, we cannot just use the results because our M is not decomposable to diffeomorphism. So, first it's obtained in quite complicated manner. But question is, okay, M does not come from diffeomorphism, but maybe we can still decompose it somehow in this way. So we thought about it and concluded that answer is no. So first of all, there is a textbook by Riskin called the Fokker-Planck equation, in which general criterion for when symmetric positive definite matrix function is decomposable as JJ transposed for some diffeomorphism or not is given in this textbook. To check it, you need to check quite complicated differential form. However, when we started to think about it, we did not know that there is such textbook, so we came up with the following result. So if we take just a matrix function of two variables and set it to be of very simple form, identity matrix times m squared of xy, where m is non-negative, is strictly positive function in some open set. And we assume it's twice continuously differentiable. Then if m is decomposable into JJ transposed, then logarithm of this function m should be harmonic. Moreover, if our open set is simply connected, it's easy to show that this condition also is sufficient condition for m being decomposable into JJ transposed. So here, all this can be shown by some very straightforward calculations. So now here our results. First, we considered a diffusion map algorithm without target measure reweighting, but with Mahalanobis kernel. And we considered a whole family of operators that can be obtained. So renormalization parameter alpha here can be any real number. So after long calculation, like 10 pages long, arithmetic back and forth, but straightforward in the sense that we just use Gaussian integrals and then manipulate them in the right manner, we arrived to quite long and terrible formula. However, if you use alpha equal 1/2, then this formula reduces to exactly this one, where L is a generator for Averdamp-Langevin dynamics in collective variables. Here is factor beta over 2. So in the limit epsilon tends to 0, the generator approximated by diffusion map with Mahalanobis kernel is exactly the generator that we want times beta over 2. Moreover, I didn't write it as separate result, but if we use target measure diffusion map, this means that if we use algorithm where we do additional measure reweighting, then we also obtain that at alpha equal 1/2, and with measure reweighting, we also obtain exactly the generator that we need. So now let's a little bit discuss the diffusion map algorithm. So what we need as input? Input is a set of data points in collective variables, set of diffusion matrices at data points, bandwidth parameter epsilon, and target measure mu. So calculation of diffusion matrices as input. This is most time-consuming operation here. So in particular for alanine dipeptide in 4 dihedral angles, it takes several hours to compute those matrices. Calculation is straightforward as I showed, however, it's the most time-consuming. What was less trivial is to understand how to compute target measure. The problem is that typical MD packages offer you computation of free energy only in 2D. But here you need it, say, in 4D if you use alanine dipeptide in 4D, or you need to know it in whatever dimension you want to handle. So this was handled as follows. So suppose we run some enhanced sampling algorithm. This means that data that we are generating are distributed according to Gibbs measure for modified potential. So in particular, it is free energy plus biasing potential. We can estimate this sampling density using diffusion maps with standard Gaussian kernel. So it is as I discussed earlier in the talk. So as a result, we have a decent estimate for this. And then we obtain target measure by simply multiplying estimate for sampling density by exponential of beta times biasing potential. So that's how we extract it. Now, all steps of this diffusion map algorithm with Mahalanobis kernel and target density are standard, so this is all just simple linear algebra operations, and run of the algorithm is very fast and straightforward. So now some numerical examples. So first, it's Moro-Cardin example. This is toy example on which we can assess accuracy of this technique. So Moro-Cardin example is has double well potential and a diffusion matrix, which is identity matrix times function, that is 1 over 1 plus Gaussian function. So this matrix is not decomposable into J times J transposed for some diffeomorphism. So I first remark that despite this is a very simple example, when we first tried diffusion map with Mahalanobis kernel, we did not get good results here. Reason is that if you look at this diffusion matrix M, this diffusion matrix M makes noise really small around the origin. This leads to saddle avoidance, meaning that transitions go from A to B go either above the origin or below it, which you can see from the reactive current. And if you try to sample data just from invariant measure, you get very poor resolution about the origin, and results also looked pretty bad for this reason. But with target measure diffusion map, with sampling using metadynamics or high temperature, results were much better. So here results. So here we used high temperature sampling, and we compare level sets of the commuter with level sets computed by finite element method. Here is current. Here we used metadynamics, which gives better coverage of samples, meaning the sampling is much more uniform. And we see that level sets of commuter look closer than the ones that we obtained by finite element method. And finally, so for using target measure diffusion maps, we do not need to know sampling density. This means that we can post-process something as we please. And we are proposing to post-process it by converting a data set into delta net. What is delta net? This means that it is a point set in which every point does not have any other point in delta neighborhood of a point. This means that we take our set of samples obtained from metadynamics, for example, and just rarefy it. Simply throw away some points. And results are even better for delta net. So here, error plots. We, for assessment of error, we used weighted error, where weights were created using probability density for reactive trajectories that can be estimated using the commuter. So for weighted absolute errors, whereas ground truth was taken, commuter computed by finite elements. These are our plots for error. So errors are functions of scaling parameter epsilon. Now, what are these vertical lines? These are heuristic estimates proposed by Tyrus Berry, I think it's Tyrus Berry's works, that gives very easy double sum test for how to choose optimal epsilon. We see that these propositions give quite good values of epsilon. So now if you look at plots, so high temperature sampling gives the worst results, the highest error. For this example, metadynamics and metadynamics data processed by delta net give close results. And if we compare estimates for reaction rate, the best results we see by delta net. We also see that estimate by using delta net data are the most robust with respect to choice of parameter epsilon. Basically, you see the graph is very flat and almost follows the ground truth line corresponding to finite element estimate.
Masha,
yes?
You're not showing results for the target temperature, but I assume that's way worse than all this stuff. Like if you've done the sampling at the target temperature, you're saying high temperature is the worst of these three.
No, there was failure. So
right.
we tried, yes, it's so disastrous that we did not include it to anywhere.
Okay. Yeah, that's what I would expect.
Yes, alanine dipeptide was much better at target temperature, by the way. But not that transition, another transition. But this doesn't work for target temperature at all. So now alanine dipeptide. For alanine dipeptide, we did two things. First, we had just numerical test for accuracy for 2D, and we did already application in 4D. So in 2D, so we see here free energy, here is a depiction of diffusion matrix, and here samples obtained by metadynamics. So here we even didn't use high temperature data because they will be under resolution in transition region. So we used metadynamics, we used delta net, and for comparison here is finite element. So again, you see that delta net gives nice results, and it can be again quantified. So here is weighted absolute error. For delta net, weighted absolute error is pretty low for quite broad range of epsilon estimates, and heuristic estimate for choice, best choice of epsilon, that is easy to check, is in low line region of the weighted absolute error. For metadynamics, results are a bit worse. Here is transition rate, which we compare for delta net and metadynamics data with what we obtain by finite elements. We again see that delta net post-processed results are in close agreement. Numerical values are right here. I will return to numerical values a bit later. So now application for 4D. So for 4D, if you project free energy to 2D space, it looks basically the same. Here is depiction of diffusion matrices. Here is depiction of committers and currents. So what we see, so here level sets of the committers are very close to what would you see in 2D. If you project into space phi and psi. However, if you project it here not to space phi theta, where theta is this angle, you also see that something non-trivial going on. And if you depict reactive current, so here is reactive current projected to phi and psi angles, and here is to phi and theta angles. And again, we see some non-trivial current. So now numerical value for the current. So here, of course, we could not do finite elements, it's 4D. But there is a recent work by Jonathan Weir and Vani and Dinner. So they used application to alanine dipeptide for testing of their approach to it, and also in this work they computed rates that can be viewed as ground truth. I understood that long unbiased trajectory was run for 1 month, at least what I learned from communication. And ground truth rate is written right here. It is 1.4 times 10 to minus 6 picosecond inverse. This is namely transition rate. It's average number of transitions from A to B over the total time. So it's not exactly the same as eigenvalue, but it is interesting to compare with your numbers. So, and this is the rate that we obtained in 4-dimensional representation. Now, if we summarize rate numbers that we obtained, we see that in 2D we have a much exaggerated rate. In 4D we have already pretty close rate to the ground truth. And this again comes to question raised in the previous talk about accuracy of effective dynamics. So here we consider effective dynamics in collective variables. It will be actually very interesting to me to try to assess it, to analyze the accuracy of this representation. What we see is that it's not bad, but can we do actually somehow better without going to very high dimensions? So, and another small moment that I wanted to bring up is that what we see that if we post-process data by delta net, results improve. So right now we are working on error analysis for diffusion map algorithms with one of my other students, and we were able to show that delta net does reduce error, but it's too early to present right now, so it's ongoing work. Hopefully in the future we will discuss it. So this is the end of my talk. Thank you.
Thank you, Masha. Thank you very much. So we have time for 2 or 3 questions. We're a little bit late.
So we've experimented with diffusion maps, well, maybe more than experimented, for within basis expansions for, you know, schemes that use time lags, so trajectory data schemes, so very different than what you're doing. But the issue that we face is one that I guess you might face as well, which is just the scaling of diffusion maps with the number of data points. I mean, you have to do some dense linear algebra, and it seems like your delta method will help that, but I'm wondering if you ran, I guess one question I could ask is, how big is the data set?
So yes, there is such problem, and how it's handled. So we always used about 10K points. So for all examples, it's about 10K points. For delta net, of course, it's rarefied, can be less. But we used such that we sparsified matrix and used sparse linear algebra, and we used such that if yes, threshold was used 3 standard deviations. So the Gaussian kernel is practically vanishes, so we zeroed out Gaussian kernels after 3 standard deviations. Then it was possible to do calculations just on simple, quite bad laptop of my student.
Right, up to 10K, okay. Yes. Yeah, I mean, these problems, maybe not alanine, but other problems, you know, like this, they're in a bit of a difficult spot where, you know, you don't really have enough data to use neural networks, I think, because the data is expensive. But yeah, we have found for diffusion maps and kernel-based schemes in general that you run into the memory required for the linear algebra becomes a problem. So they work better for small data sets, but then, you know, there's an in-between that where the problems might, it's not clear what to do.
So my comment on this as follows. So for diffusion maps, their power is that they can work well in high dimensions as soon as a data set is intrinsically low dimensional. So, and as I said, the most expensive part is calculation of actually those diffusion matrices. For neural networks, if you want to use dynamics in collective variables, there will be exactly the same problem of computing diffusion matrices. However, regarding neural networks, so there are works of Haizhao Yang and collaborators about approximation theory for neural networks. So they showed that actually you can represent classes of functions, smooth or just continuous, with neural networks using exponentially few points. So this shows that in general, if you can use not that many points in high dimensions, as soon as functions that you want to represent is smooth.
So that's saying there is a fit that's good.
Yes, so for neural networks, so it depends on what activation function you use. So you can, it looks like you can beat curse of dimensionality. So I'm just exploring this topic. I cannot say too much, but that's what I understand. With ReLU, you cannot beat curse of dimensionality. With, say, Tang, you can. And for diffusion maps, yeah, it depends on intrinsic dimension of the system.
Maybe a final question before we go for lunch. If not, thank you again, Masha.
So there is a list of
restaurants on the website. There are plenty of choices.